Okay, so please confirm that you can see the presentation. Hello.
Yes, sir.
Okay, so let me just briefly recall the sequence of lectures that we followed. We went up to Gauss's law, the basic principles of Gauss's law, a basic understanding, and I supplied you notes up to page 66. Then this set of notes starts from page 72. I am skipping a little ahead. I shall later come back to page 67 and onwards, but for the time being, I'm skipping a little ahead to discuss certain topics pertaining to symmetries with respect to Gauss's law. So there are three basic symmetries that we shall take up, namely the spherical symmetry, the cylindrical symmetry, and the plane symmetry. So in each of these, there are some basic, simple applications of Gauss's law. So I shall be talking about that. So let us see. So the first topic that I shall take up today is about spherical symmetry, how you apply to Gauss's law within a Gaussian surface. So there's a hollow spherical shell of radius R0. This is the shell. So it's empty inside. It's just like, let's say, a copper or a brass shell. So it's a spherical sphere, but it's empty inside. Okay, so it just has a shell. Charges are made to reside on the surface. So all these plus charges, let us say, and they're all sitting on the surface of the shell. Total charge residing on the surface is capital Q. And so you shall now have to find the electric field due to these charges in three cases. Let us see what they are. First is R less than R naught. This here written over here is R. It looks like E. I'm sorry about the bad handwriting. This is R less than R naught. It is not, it is looking like E. This is E, of course, but this is R. R less than R naught meaning that you are inside the shell. In all of these cases, the basic approach is to write E dot dA integrated over the surface. What is the surface area element of on a spherical surface? The area element on a spherical surface is r squared sine theta d phi r cap. Okay. And the electric field is a function only of r and acting along the r cap direction. So this thing has got r cap, and dA also has got r cap. So r cap dot r cap will be equal to 1. These are points we have discussed many times earlier, but the integration is over theta and phi. So anything that depends on r should be treated as a constant. And so E comes out of the integral and integrated over the full surface. It is E into 4 pi r squared. 4 pi r E into 4 pi r squared, Gauss's law in integral form. It says that the closed surface flux of the electric field is equal to charge enclosed within that closed surface divided by epsilon naught. But if you are at a radius that is less than that of the shell, then charge enclosed will be equal to 0, because the charges are on the surface of the shell. If you draw a Gaussian surface within the shell, you will enclose 0 charge. Therefore, charge enclosed is 0, therefore E is equal to 0. Charge enclosed by epsilon naught divided by 4 pi r squared, 4 pi epsilon naught r squared. That's equal to 0. So that's the sort of thing that happens inside a Van de Graaff generator. On the surface of the generator, you can have a huge gathering of charge at a very high potential, but within the generator, if you stand within the shell, if you stand, you will not feel anything. So that's because inside the shell or inside the enclosed surface, the electric field is equal to 0. Okay, next case. When you draw your Gaussian surface on the surface of the sphere itself, in that case, R is equal to R naught. Okay. So E dot dA, it shall be E into 4 pi R naught squared, because now earlier R did not have a defined value except that it's going to be less, it will be less than R naught. Apart from that, it doesn't have a defined value, so you just leave it as R squared. But here, the value is precisely given, it's R naught. So E to 4 pi R naught squared is equal to Q by epsilon naught, therefore E is equal to Q by 4 pi epsilon naught R naught squared, and that's equal to E naught. Okay, so that's for R equal to R naught. Of course, not to lose sight of the fact that, just to stress on this thing, that the surface area element will be 2 cross 3. You take this and this, cross them on a spherical surface, and this is what you get. Okay. The next case to take, see, there are three cases, sub-cases here for a particular topic. You have a hollow spherical shell of radius R naught, once within the shell, once on the shell, and once outside the shell. So now you've gone outside the shell, R greater than R naught. So E dot dA, E to 4 pi R squared is equal to, you are now enclosing the total amount of charge. Charge in the second case also, you're enclosing the total amount of charge, that's capital Q. Here also you're enclosing the total amount of charge, capital Q, but you've gone outside, R greater than R naught. So E is equal to Q by 4 pi epsilon naught R squared. Okay, and then after that, you can just make a little fancy manipulation. You just multiply by R naught squared, divide by R naught squared, and so Q by 4 pi epsilon naught R naught squared is what you have defined over here as E naught. And so that is how you write it. So basically, here you are. You have that's the situation. Now, earlier we talked about a hollow spherical shell. Now we shall talk about a solid charged sphere radius R naught. E dot dA, closed surface integral, E into 4 pi R squared is equal to charge enclosed by epsilon naught. Whenever you see a spherical shell, this is just E multiplied by the total surface of a sphere, 4 pi R squared. That's how you should start, is equal to charge enclosed by epsilon naught. Okay, so solid charge sphere radius R naught. So inside the sphere, you have charges. Earlier, since in the previous case, it was a hollow shell, so the charges were on the surface. But now there is conducting material inside, let's say a copper sphere or whatever. And there, you have injected this entire region with charges. There you have all the charges within. And so what you have to do now is to apply the same principle as earlier on at three values of the radius, namely R less than R naught, R equal to R naught, and R greater than R naught. In all of these three cases, you shall have to estimate the electric field. So E to 4 pi R squared is on the left-hand side. What about the right-hand side? The right-hand side is charge enclosed by epsilon naught. So here, this dotted circle represents the Gaussian surface that you have drawn. So only the charges enclosed within that surface should matter. Only the charges enclosed when this surface has got a radius small r, which is less than r naught. Okay. What is the charge density? Charge density is equal to Q divided by 4 third pi r naught cubed. What is 4 third pi r naught cubed? That's the total volume of the sphere. And Q is the total charge enclosed within the sphere. So you take the charge density to be constant, which is not a bad approximation, because all the charges would tend to repel one another and since they are of the same type, they will repel one another and they'll try to get as far away as possible from one another. But in the process, all the charges will end up making end up with equal spacing among themselves. No single charge will be any closer or any farther than any of the other charges. So that's here. That is what you have over here. Now, what is the total charge enclosed within this dotted circle? It will be rho, charge density, multiplied by the volume of the dotted circle, which has a radius of r. So 4 third pi r cubed into rho by epsilon naught. And so now let's see, you can actually do a lot of cancellation business, but I'd rather not get into all that. What I would do is that I would multiply this equation and divide this equation by r naught cubed. So I have got 4 third pi rho r naught cubed, and then I'm dividing by r naught cubed. And then you have a 4 pi r squared from the left-hand side that comes down over here. You have 4 pi epsilon naught. And this r squared and this r cubed will cancel, and you just have a single r here. Okay, and this will be the total charge capital Q. Rho into this volume will be the total charge capital Q divided by R naught squared into R by R naught and Q by 4 pi epsilon naught R naught squared you define as E naught. So that is E naught, and so E is equal to E naught into R by R naught, which is a linear relationship. Then R is equal to R naught. Okay. It's a very simple thing, really. When R is equal to R naught, Q enclosed is equal to capital Q, and R is equal to R naught. You can get it from here straight away, or you can also get it from here. R is equal to R naught, and you'll have a cancellation, and you'll just basically have the same formula. E is equal to Q divided by 4 pi epsilon naught R naught squared, E naught, which is the same thing as your E naught in the previous example. And then R greater than R naught. E to 4 pi R squared, that's equal to, again, you have gone outside the sphere. You are enclosing all of the charge, total charge, capital Q. So that is what you have. Uh, and so capital Q by 4 pi epsilon naught R squared. Again, I'm multiplying and dividing by R naught squared. And this shall be E naught by into R naught by R whole squared. So basically, this will be inverse square. You see, E naught is a constant quantity, R naught is a constant quantity. So basically, E is proportional to 1 upon R squared. So that's an inverse square formula. Whereas here, it's a linear formula. And at R equal to R naught, it's E naught. So basically, if you were to graphically plot this, at R equal to R naught, it's E equal to E naught. Before that, E starts with a linear relationship, ends here, and then thereafter it falls off as 1 upon R squared beyond that. Okay, so we have discussed two cases of the spherical symmetry. The third case that we would like to take up now is of two concentric shells, hollow shells of radii R1 and R2. This is a very simple case. Hollow shells you have. The first one has got the inner one, concentric meaning both have the same center. The inner shell has got a radius R1 with charge Q1 residing on its surface. The outer shell has got a radius R2 with charges residing on its surface. So E into 4 pi R squared is equal to charge enclosed by epsilon naught. Okay, R less than R1. You have that thing. Meaning you are inside. You are enclosing no charge. You can just, in this formula, all you have to do is to put the value of charge enclosed. And if there is a precise value of the radius, for instance, in the second case, you have R equal to R1, you put that. So wherever you have an R equal to something, you have a value that you can put in the formula. Otherwise, if R is greater than or less than or whatever, then you don't have to put any value to R or any number. Oh. Okay, R equal to R1, charge enclosed will be Q1. R equal to R1 meaning that you are on this surface. Charge enclosed is Q1. R between R1 and R2 in this space between the two shells. So charge enclosed continues to be Q1. On the second shell, R equal to R2. Charge enclosed is now Q1 plus Q2. Total charge, Q1 plus Q2. R greater than R2. You have gone outside the outer sphere. When you've got charge enclosed continues to be Q1 plus Q2. So basically you've got 5 values of charge enclosed and 2 values of the radius. The latter 2 values being R1 and R2, and charge enclosed will have charge 0, Q1, Q1, Q1 plus Q2. So basically like that. Well, actually charge enclosed has got 3 values in a way also. Okay, so as I've said, count only the charge within the Gaussian surface. That's always this basic logic to follow. Okay, so we have discussed some simple cases of spherical symmetry. Now we shall take up the discussion on cylindrical symmetry. Let's see. The first thing that we shall take up is of an infinitely long charged wire of constant charge per unit length lambda. So here you have a wire. Charges are made to sit on the charges of the same sign, let's say positive charges. So they are made to sit on this wire. The charges are not moving. If they were, then you would have had a current. But we are not talking about a current right now. It's just a wire full of charges. Okay, they are made to sit on this thing. So at any point on the wire, the field lines going out will be radiating outwards, but be confined to the plane, the equatorial plane over here. That is what you have. It's on this plane that the field lines will be confined. Okay, unlike a point charge, in the case of a point charge, the field lines will go in every direction and the symmetry will be spherical. But here, the field lines are symmetric about the axis. And the field lines, so suppose you have this black dot over here representing a charge. So the field lines due to this charge will not come above this disk or go below this disk. They will always be confined to this equatorial disk, this disk. So that's what you have. And as such, the electric field lines will depend only on the cylindrical coordinate S. So going out of this axis, going in any direction, it depends only on S. And the electric field can be written as S cap. Okay. What about the area of this window? The area of this window is S d phi dz S cap. So this integral is over phi and z. So as has been written over here, integrate over phi and z. So this integral is over phi and z. If that is so, then anything that depends on S will come out of the integral. S cap dot S cap will of course be equal to 1. And so the integral will be Es into S outside. Then you have d phi and dz. D phi is integrated from 0 to 2 pi. Dz is to be integrated from 0 to h. Basically, you will just have E into S. This will give you 2 pi. This will give you h. And that's equal to charge enclosed by epsilon naught. Okay. So within this cylinder, how much charge is enclosed? It's the charge that is lying from this point to this point, from the top disk of the cylinder to the bottom disk of the cylinder. That's the total amount of charge that you have to take into account. So basically, all you have to do is look at the charge per unit length lambda, charge per unit length lambda into h. H is the height of the cylinder. So lambda into h. So E into 2 pi sh is equal to this charge enclosed is lambda h by epsilon naught. So the h's will cancel on both sides. And E is equal to, well, I mean, it is with the h's cancelling, you will have lambda divided by 2 pi epsilon naught s. But I'm multiplying and dividing by a 2 so that it becomes that familiar 1 by 4 pi epsilon naught. That formula, and that into 2 lambda by s. Okay, and of course one last point is that this window that you have will be the outcome of 2 cross 3 s d phi dz. S d phi dz, phi cap cross z cap will give you s cap. So this window is the outcome of taking the second and the third terms in the line element. Okay, so that was a simple wire and with an imaginary Gaussian surface, a cylindrical Gaussian surface enclosing it. Now, instead of a simple wire, we talk about a solid, infinitely long charged cylinder of radius S naught. Volume charge density is rho, charge line density is lambda. I shall come to this lambda part later. So basically what happens is that first let us try to go back to our familiar example of a spherical symmetry. If you, let's say, stand outside the Earth, you will feel the Earth's gravity, but it doesn't matter how the matter of the Earth, how the Earth matter is distributed. The Earth could be a sphere, or the entire Earth could be collapsed at a point at the center. It wouldn't matter to you. As long as you are standing outside, all you will feel is the same. You will feel the same gravitational pull in both the cases. Okay, now the same idea applies to the cylindrical symmetry, except that there is a slight geometrical difference. If you stand outside a cylinder that is full of charges, so from your point of view, it would look like that all the charges have collapsed at the along the central axis. Suppose you have this cylinder here. It is full of charges and you are standing outside. You are another charge or whatever, and you experience the attraction or the repulsion. So as far as you're concerned, this cylinder might as well have collapsed at the center along this line. So you have got, in that case, although you're working with the cylinder, but viewed from outside, it would look like that the charges have gathered all along a line. So appears collapsed on the axis. So what is the total charge contained within this cylinder? That will be the volume of the cylinder multiplied by the density. So volume of the cylinder has got a radius of S naught. Volume of the cylinder will be pi S naught squared. Pi S naught squared is the disk area of the cylinder. That multiplied by H will give you the volume of the cylinder. That into rho is the total charge enclosed. But if you look at the same cylinder as a collapsed line of charges along the axis of the cylinder, then the same thing could also be written as lambda into H. So total charge within the cylinder can be written in two ways, but since they're the same thing, if you equate these two, the H's will cancel on both sides and lambda is equal to rho into pi S naught squared. So that's one important point of information that we shall use later for our algebraic manipulations, the relationship between the line charge density and the volume charge density. Okay, so let us now take, as before, we shall take up three cases, that as in the case of the sphere, here also we shall take up three cases. What are the three cases? Once the electric field outside the cylinder, the electric field on the surface of the cylinder, and the electric field within the cylinder. So outside the cylinder, S is greater than S naught. E into 2 pi SH. Okay. That is this integral. E into 2 pi SH. That will always be the same. For cylindrical symmetry, this is the equation you have to have, E into 2 pi SH. And for spherical symmetry, E into 4 pi R squared. So that is what you have. So E into 2 pi SH is equal to, what is the total charge enclosed? Total charge enclosed will be the total charge in the cylinder, which is rho into pi S naught squared H by epsilon naught, and that's also equal to lambda H by epsilon naught. Okay, and so basically you can now carry out a little cancellation and all that. So H here and H here will cancel, and you'll just have lambda by 2 pi epsilon naught S. Then you can again multiply and divide by 2 and multiply and divide by S naught. So E naught is equal to 2 lambda divided by 4 pi epsilon naught into S naught. Okay, and that's how you're defining E naught, 2 pi by 4 pi epsilon naught into S naught. And so E here will be equal to this E naught into S naught by S. So that is what it is. So you can see that the electric field outside the cylindrical configuration is going off as 1 upon S, inversely proportional to the distance. So this is the same thing. E is equal to this 2 pi, 2 lambda by 4 pi epsilon naught. This whole thing is just like, I mean, I could have just, I mean, here if I cancelled the two S naughts, this and this, these two, if I were to not keep, just cancel them, and it will be 1, then only this part will remain, and that is equal to the case that you have over here, twice lambda by 4 pi epsilon naught S. So that is as in the case of an infinitely long charged wire. Why should that be so? Because as I said, outside a cylinder, if you're standing, then from your point of view, the cylinder could just have been collapsed to a wire on the central axis. So that's why in both the cases, you will see the same mathematical formulae. Okay, now S is equal to S naught. E is equal to 2 pi sh, the left hand side, but S is now carrying a precise value of S naught. So you put that thing 2 pi S naught h, and the right hand side will be rho pi S naught squared h by epsilon naught. Okay, and that's also equal to lambda h by epsilon naught. So once again, this h and this h will cancel, and E is equal to 2 lambda by 4 pi epsilon naught S naught, and that is equal to E naught. This is what you have. And then in the last case, S less than S naught, here you have to be a little careful. E into 2 pi sh, left hand side, is equal to charge enclosed by epsilon naught on the right hand side. But what is the charge enclosed? The charge enclosed will be, if you have drawn a Gaussian surface which is smaller, whose radius is smaller than that of the actual cylinder, and the radius is S, then you only need to worry about the charge enclosed within that cylindrical Gaussian surface, which is rho charge density multiplied by pi s squared into h. And that is what it is, rho pi s squared into h. And after that, cancellations once again. But I haven't immediately canceled it. I've written 2 pi sh epsilon naught rho pi s squared is here into h, and then s naught squared by s naught squared I have written over here. Okay, once you have that thing, next task will be, we will just write this thing in a simpler form. What have we got over here? Rho pi s naught squared h. Rho pi s naught squared h, rho pi s naught squared h is equal to lambda into h. That is what we have put over here. We put a 2 here, and we put a 2 in the denominator, so it will be 2 by 4 pi as here into this whole thing is now lambda into h by epsilon naught. Okay, and then these two h's will cancel, this and this will cancel, and this s and this s squared will cancel to give you an s. And what we will do is that this S naught squared will be split into two parts. We have got an S naught here and an S naught there. These two H's will cancel, and you'll just have 2 lambda by 4 pi epsilon naught S naught. Okay, and that will be E naught. So that's a linear relationship. E goes as constant into S, the linear function of S. This is just like y is equal to m into x, a straight line passing through the origin. So inside this cylinder, there's a linear variation of the electric field. Outside the cylinder, the electric field falls off as inversely proportional to the distance from the central axis of the cylinder. Once again, if you have to plot that thing graphically, at S equal to S naught, E is equal to E naught. And this is the straight line that goes up. The linear part, which is this formula, within S equal to S naught, and then after that it will fall off as in an inverse proportionality behavior, inversely proportional. That is what you have, S greater than S naught. That is what you have. Okay, now let us go to the third case. The third case will be far easier than what you have discussed over here. This always in the case of the solid sphere as well as the solid cylinder, it's the thing that is within the for a Gaussian surface within the actual surface that poses a little challenge, but otherwise the rest of the other problems are quite simple. So here you have a situation, you have a hollow cylinder of radius S naught. Okay. E dot dA is equal to E into 2 pi sh. That's equal to charge enclosed by epsilon naught. That's always the first thing to begin with. Okay, S less than S naught within here. Charge enclosed is equal to 0. S is equal to S naught. Charge enclosed is equal to capital Q. S greater than S naught. Charge enclosed is again capital Q outside the hollow cylinder. So when S is less than S naught, charge enclosed is equal to 0, E is equal to 0. When S is equal to S naught, E is equal to Q divided by 2 pi S naught H by epsilon naught. That's E naught. And when S is greater than S naught, you can't put any value for S, so you leave it as S over here. So Q divided by 2 pi H epsilon naught. and then this S naught is written over here. You multiply it by an S naught, so S naught by S into E. So those are the three cases you have to work with. So hollow cylinder is quite easy. The last case that we shall take up is that of two concentric hollow cylinders of radii S1 and S2. Let's see how. E dot dA is equal to E into 2 pi sh. Okay, that is what you have. As equal to charge enclosed by epsilon naught. Okay, and so you have got this Q1 for the inner cylinder, Q2 for the outer cylinder, S1 is less than S2, E into 2 pi sh is equal to charge enclosed by epsilon naught. And then when S is less than S1, charge enclosed is 0. S is equal to S1, charge enclosed is Q1. Between S1 and S2, charge enclosed continues to be Q1. On S is equal to S2, charge enclosed is Q1 plus Q2. And outside the outer cylinder of radius S2, charge enclosed is Q1 plus Q2. So at S is equal to S1, E will be equal to, just look at this formula, Q1 divided by 2 pi S1H epsilon naught. So that is what you have. And at S equal to S2, E is equal to Q1 plus Q2 divided by 2 pi S2H epsilon naught. So this and this have got precise values of precisely defined values of S, and therefore I have written it over here. So we have finished the cylindrical symmetry. Let me just quickly recall our discussion. Try to follow, remember this discussion. In the case of spherical symmetry, there are three cases you have to talk about, namely hollow spherical shell, solid spherical object, a solid sphere with charge distributed uniformly within. So hollow shell, solid sphere, and the third is two concentric hollow spheres. So there are three different systems you have to discuss. And in the cylindrical case, there are four such systems. First is a long wire, infinitely long wire, just a wire, nothing else. Second is a solid cylinder. So just like the other three cases, as I said, under cylindrical symmetry, you will have four systems. The first is a long, infinitely long wire. But the other three things are the same as the spherical problem, except that instead of a sphere, you shall talk about a cylinder. So you'll have a hollow cylinder, you'll have a solid cylinder, and you'll have two concentric hollow cylinders. So those are the things we have discussed. We shall now look at the last case of symmetry, namely plane symmetry. Let us see. In plane symmetry, earlier you had charges on a spherical surface within a spherical inside a solid sphere, or charges on a cylindrical surface, infinitely long cylinder, or charges within a solid cylinder. But now we have no such thing. You just have a plane sheet as in this diagram, xy plane. So this is x direction, this is y direction, and this is the vertical z direction. So along the z direction, now let us see, you have got charges made to sit on this plane. Okay. These charges will throw field lines above the plane and below the plane. So let's say a copper sheet, infinitely long copper sheet, both along infinitely extended, both along the x and the y directions. This copper sheet. Okay, and the charges are made to sit on the surface of this copper sheet, and so they'll be throwing field lines above and below the plane. So this will be like a bed of nails. Okay. What you do is that you define a small Gaussian pillbox of area A. So this is a box. What do I mean by a pillbox? A pillbox is a small box in which you keep medicine, small pills, homeopathic pills or whatever. So you have some box like that. The box is embedded in the plane in such a way that half of the box is above the plane and half of the box is below the plane. And the plane is cutting this box into a top half and a bottom half, like that. And the charges are distributed uniformly with a surface charge density of sigma. Okay, so that is what it is. I've written a question over here. Why just the vertical field lines? You'll say that shouldn't the charges be going all along in every direction? Indeed, if you have an individual point charge, then the individual point charge will be throwing field lines in every direction, not just above and below. But then on a plane, there are an infinite number of such charges and two charges neighboring each other. Try and follow this thing. We'll be throwing field lines that will be oblique to the plane. So you have, let's say, a charge over here. It'll be throwing field line in the right direction, a right inclined direction, and then you have a charge slightly to its right. It'll throw a field line to the left direction. So all the field lines will have both vertical and horizontal components in every direction. So if you just decompose all the field lines into their respective vertical and horizontal components, try and follow this discussion, understand this discussion, this point I'm making here. All the horizontal components will cancel out. And if all the horizontal components cancel out, what will survive will only be the vertical components, and they'll be sticking up above the plane and sticking down below the plane. So this will be like a double bed of nails. On a bed of nails, you have the nails pointing up. So this is something like that. So you have field lines going above and field lines going below, being thrown below. Now these field lines, E, are dependent only on the z-axis and pointing along the z-axis. So E is just a function of z going along the z direction, up and below, so z cap. So E dot dA, so total surface. So we are just interested in the area confined within this pillbox. The area is capital A. Capital A, so E dot dA will be capital A. The E doesn't depend on X and Y, so E is just dependent on Z. What is this area dA? Area element on this sheet, plane, XY plane, area element will be dx dy z cap. So Ez z cap dot dx dy z cap dot z cap will be equal to 1. Anything that depends on z will not participate in the integration because the integration is over x and y. So basically E will no longer be a part of the integral. It will come out, and this area element integrated over the full face will give you capital A. dA integrated along the x and the y directions will give you capital A. But I've got a factor of 2 as well. Why have I put a factor of 2? Simple answer, because now there are two open surfaces, one above and one below. So that is why. So E dot dA will give you, area is E, but then there is also a bottom face to this pillbox. So that's why I have to put a factor of 2. That is the answer. So E dot dA is equal to charge enclosed by epsilon naught as usual. But E dot dA we have just found is equal to 2 A into E. So here it's written 2 because of two free surfaces. That's the answer. Why 2? Here's the answer. 2 into A into E is equal to charge enclosed by epsilon. And what is charge enclosed within this pillbox? Surface charge density is sigma. Area is capital A. So charge enclosed within this pillbox. Within this pillbox, the charges are actually lying on this plane. Follow the cursor. This line and this line defines a little surface, a rectangular surface of the pillbox. Remember, the top face of the pillbox is a little above the plane and the bottom face of the pillbox is a little below the plane. The plane itself dissects the pillbox into a top half and a bottom half, like something like a sandwich. Okay, two slices of bread, one above and one below. And so that plane here contains how much charge? Namely sigma, which is the surface charge density into the cross-sectional area of the box. So that is sigma into A. Thereafter, the two A's will cancel out. Capital A's will cancel out here and here. They will cancel out, and E will just be equal to sigma by twice epsilon naught. Okay, so E will be equal to sigma by twice epsilon naught. That's the magnitude part. If I were to write it vectorially, I'll write it as n cap. Why n? why not Z cap? And I'll come to that discussion. So E will be equal to sigma by twice epsilon naught n cap. What is n cap? N cap is a normal vector to any plane surface. N as in normal. Normal vector to any plane surface. In this case, the plane surface is the xy plane, and therefore n cap shall be z cap. But generally speaking, any plane surface you take, it doesn't have to coincide with the xy plane. It can be inclined, an inclined sheet, inclined with respect to the xy plane. Anything, whatever you have, if it you can write it as n cap, so sigma by twice epsilon naught n cap, and similarly here also sigma by twice epsilon naught minus n cap. What about minus n cap? The field lines pointing below. For field lines going above in the positive direction, positive normal direction, it will be plus n cap. Field lines going below in the negative normal direction, it will be minus n cap. So that is what you have. So it's a constant electric field density. Why constant? Because you can see on the right hand side, sigma does, I mean, the electric field has no variable, nothing like x, y, or z or anything. So regardless of wherever you are, how far or how close you are to this electric sheet, I'm sorry, to this conducting sheet, the electric field will not change in its value. So that is an important lesson to. I've written something over here. Compare with the cylindrical and spherical symmetries. So this is the constant electric field intensity that you have. Why am I asking you to compare with the cylindrical and spherical symmetries? Let us just go back to that discussion a little. I'll just stop sharing this presentation, and I shall take up something that I discussed with you already in here. I'll start the presentation. Just give me a minute. Start the new presentation. Please just give me a minute. I hope you can see the presentation. Can you please confirm?
Yes, sir.
Okay, thank you, thank you. So here, just this is something that I just touched upon before the examination. It was not really a very important part of the examination. So I thought I'd just, since I was giving you the notes, I talked about it. Here I shall talk about it in some greater detail. So here you have a Gaussian surface. First, let's just, so Gauss's law and some geometrical aspects. I told you with respect to the plane thing that in the case of the plane, regardless of how far or how close you are to the plane, the electric field will not change. However, in the spherical and cylindrical symmetries, the electric fields will change. Why so? Let's now try to see. So first, let's just discuss this thing. What is a Gaussian surface? As I said, it's an imaginary surface drawn to enclose charges according to the symmetry of the physical system, spherical symmetry, cylindrical symmetry, etc. So here's the real spherical surface here's a real sphere of radius capital R. You can draw a Gaussian surface within an imaginary dotted surface. Within that, this will be the Gaussian surface, and only charges enclosed within this surface will matter. And similarly, you can draw another Gaussian surface outside, and it will be the surface that will enclose all of the charges within this real surface. Okay, charge distribution in Gauss problems. Next thing. As I said, we have taken the charge densities in all the cases to be constant. That is not an unreasonable approximation. Why? Because charges of the same type are distributed uniformly on surfaces or throughout volumes due to the same degree of repulsion among them. So basically, if you have charges of the same type, they'll repel one another, and eventually they will settle into a configuration whereby they will not get any two charges will not be any closer or any farther between themselves than any of the other charges. As a result, they will maintain the same spacing and they'll be uniformly distributed. So that is what it is. Now, here's this point. As I said, just in the previous slide, I said that compare with spherical and cylindrical cases. That is what we are going to do. Gauss's law on a spherical surface. A sphere has got only one surface. So it's a very symmetric and simple surface to work with. Symmetric about the center point, natural coordinates are r theta phi. Area element of outer face is r squared sine theta d phi d theta d phi r cap. From the outside, charges appear to collapse at the central point. Okay, fine. Now, here's the very important thing. The central point, the source has got 0 dimension. But E will go off as 1 upon r squared. So the source has got, viewed from the outside, it will look like all the charges have gathered at the center, at the central point. A point has got 0 dimension, whereas the electric field will fall off as 1 upon distance squared, 1 upon r squared in this case. R is the distance from the center. What about cylindrical surface? You make a note of this 6th point carefully. I shall come back to it. The cylindrical surface. A cylinder has got 3 surfaces. You have a curved face, you have got an upper face, and you have got a lower face. 3 faces you have. It's symmetric about the central axis. Its natural coordinates are s phi z. Area element of the outer curved face is s d phi dz s cap. Of the top and bottom faces, ds s d phi z cap. Okay. These notes I supplied you already. So it should be familiar to you. From the outside, charges appear to collapse on the central axis, not at a point. In this case, in the case of a sphere, if you're standing outside, it would look to you that the charges have collapsed on the central point. But here, it would look to you that they have collapsed on the central axis. And the natural coordinates are s phi z. Sorry, from the outside, charges appear to collapse on the central axis. That is what you have. The source of charges is this axis now. And what is the dimension of an axis? It's a line. The dimension will be one-dimensional. It's a one-dimensional object. But the electric field will fall off as 1 upon s. 1 upon s is the way the electric field falls off. You notice something? If the source is 0 dimension, the electric field will fall off as 1 upon distance squared. If the source is one-dimensional, the electric field will fall off as 1 upon distance raised to the power 1, s raised to 1. So dimension is 1, length raised to 1. So the dimension plus the power of the length will always remain a constancy. 0 here and 2 here. 0 plus 2, 2. 1 here, source is one-dimensional, dimension of the source is 1, and the strength of the electric field is also distance raised to 1. First power 1 and dimension 1. 1 plus 1, 2. And one last point, but I'll return to these 2.6s in the cylindrical as well as the spherical case. One last point is that from each point on the central axis, the field lines spread out radially on the equatorial disk. Why so? You have these field lines on a plane, right? So you have this line of point charges. First, let me finish this discussion. You have these lines of point charges. Suppose you did not have any other charge except one charge. Then the field lines due to the charge will go in every direction, up, down, left, right, everywhere, obeying a spherical symmetry. But suppose you bring another charge above it, then that charge will be throwing field lines below. So all the field lines could be decomposed into a vertical component along the axis and a horizontal component perpendicular to the axis. So basically what we'll have is that all the vertical components along the axis, up and down, will cancel out. And what will survive are only the horizontal components which are normal to the axis. As a result, when you have a line of charges, the field lines are all confined to this disk, the plane. that way. They will not go above or below. Any point, any charge on a line of charges will throw field lines which are symmetric about this axis. Symmetric about this axis. The field lines will be confined to the plane. Okay, so I hope you have understood this point. It happens because the vertical components of the field lines will cancel out. Now let's come back to this thing. The central axis is one-dimensional, but the electric field line will fall off as 1 upon distance raised to 1. Here, the central point is zero-dimensional, but the electric field will off as 1 upon distance squared. Here it is distance raised to 1, and here it is distance squared. So the dimension of the field line plus the power of the distance, the inverse power of the distance, always maintain constancy. Zero dimension, square power, 0 plus 2. One dimension, first power, 1 plus 1. Both 0 plus 2, 1 plus 1 will be 2. Now in the case of a plane, the thing that we finished discussing in the last slide, in the case of a plane, what is the dimensionality of a plane? It's two-dimensional. A plane, XY plane, is a two-dimensional object. If it's a two-dimensional object, then the dimension of the plane will be 2, but the electric field will fall off as 1 upon distance raised to 0. So here you have 0 plus 2. Here you have 1 plus 1. In the case of a plane, the dimension of the plane is 2, therefore the electric field line will fall off as 1 upon distance raised to 0. What distance raised to 0 is 1. Anything raised to 0 is 1. So basically, if the distance raised, you have distance raised to 0, meaning the electric field lines become a constant quantity. I'll stop the sharing here. I'll go back to that discussion now. Sorry, just a minute. Here. That is what you have. This is the source. The plane full of charges is the source. I hope you can all see this presentation. I hope you can. So I'm not asking you to confirm it. If you can't, then you let me know. So the source is this plane full of charges. So the source has got two dimensions. Therefore, the field lines will fall off as 1 upon distance raised to 0, but distance raised to 0, anything raised to 0 is 1, which is a constant quantity. So the electric field doesn't change. So that's how you should see. That's the symmetry. Anyway, I have finished the discussion on these basic ideas of symmetry. Today we shall start a new topic. Please let me just close these slides and start with a new set of notes. So I have discussed the symmetry issues, and I have discussed the kind of things that you should geometrically intuit. Let me just begin the new discussion. Sorry, just a minute. In a minute, I'll start the new presentation. Please just bear with me. Can you please confirm that you can see the new presentation? Hello?
Yes.
Can one of you? Okay, okay. Thank you. Thank you. Okay, so before the examination, I gave you notes up to page 63. One of you, please mute the mic. It's causing some distraction. Thank you. Please mute the mic. Yes, I have muted it for you. Okay. So page 66 is what I gave you, the notes up to page 66. Today, we shall start with page 67 after having finished all that. Just I went a little ahead of the story because that's not really a very important theme. You could have, that's just wanted to give you some idea. Anyway, so here we are. Here you have Poisson's equation. How to begin with this thing? We are still talking electrostatics. You have a static distribution of charges. In the case of a static distribution of charge, let us just say take a single charge, one charge. You don't even have to worry about a distribution of charges. Uh, a single charge will be q by 4 pi epsilon naught r squared. Well, that will be the electric field due to the single charge. Q by 4 pi epsilon naught r squared into r cap. So similarly, if you have a static distribution of charges and you have enclosed all the charges within a spherical Gaussian surface, as in this case, you have all these charges enclosed within that sphere, then you will have just E being a function of the radial vector r, 1 by r squared r cap, fr, r cap. So for such a distribution of charges, curl of the electric field will be equal to 0, because we have discussed this thing. If it's a central field, depends only on the radial vector r, then curl will be equal to 0. Okay, and if you write curl of this thing is equal to 0, then you can also, by the same principle, we have discussed this thing as a part of our discussion on potentials. We also know that the curl of the gradient of a function, scalar function, is equal to 0 vector. Therefore, we can write the electric field as the gradient of a scalar function, capital V. That is what we have written over here, minus gradient V here. The minus sign happens because of some conservation issues, but mathematically you would not be wrong if you did not put in that minus sign. The minus sign is a physics input. But then Gauss's law of electrostatics in differential form also tells you that the divergence of E is equal to rho by epsilon naught. This differential form of Gauss's law of electrostatics, divergence of E is equal to rho by epsilon naught. So just follow the logical flow. E is a function only of R. It's a vector function, R, and directed along R cap. Therefore, curl of E is equal to 0. If curl of E is equal to 0, then you can write E as the gradient of a scalar function, because curl of the gradient of a scalar function is also equal to 0, the latter being a mathematical principle. And I have put a minus sign also because of physical reasons due to the conservation principles. Okay, so E is equal to minus gradient, the scalar function. Gauss's law of electrostatics says divergence of E is equal to rho by epsilon naught. All we have to do now is to substitute this vector E with this negative gradient of a scalar function. So divergence of the negative gradient of a scalar function is equal to rho by epsilon naught. V is the scalar potential. Okay, so del dot del V is equal to minus rho by epsilon naught. This minus sign has now gone to the right hand side. You have got minus rho by epsilon naught, and this should not surprise you. All that you should do is to consider shifting the brackets a little. You shift this bracket here, you shift this bracket here. This will look like divergence of the divergence of V, and divergence of, the divergence of the gradient of V. And del dot del will be equal to del squared. So this is the Laplacian operator. Del squared V is equal to minus rho by epsilon naught. So this equation, del squared V is equal to minus rho by epsilon naught, is known as Poisson's equation. And Laplace's equation is a special case of that, whereby you are studying. Remember, what did I tell you? We are working with the differential equation. Differential equation is a local description. A differential equation follows variation from one point in space to another. That is the use of a differential equation. So here you have got the differential equation being applied on a region where you have charges. If you have charges, then you can write a density function for the charges, minus rho by epsilon naught, density of charges minus rho by epsilon naught. But then electric field can be in regions where there are no charges. Charges give rise to the electric field, but then the electric field lines will travel far out of the region where you have charges into vacuum throughout all space. So suppose you are now locally looking at a region in space where you have the electric field, but the source charges of the electric fields are at some point, some other point far away. So in that case, you will have zero charge, therefore zero charge density. In which case, rho will be equal to 0, and you will just have del squared V is equal to 0, which is Laplace's equation. So Poisson's equation is del squared V is a scalar function, scalar potential function, minus rho by epsilon naught, and this is rho is equal to 0, del squared V is equal to 0. Laplace's equation holds in a charge-free region in space. Okay. I'll just touch on something important over here. Why are we complicating things? We could have ultimately, our purpose is to find the electric field. So why are we going into a potential business? The answer is simple mathematical expediency. What do I mean by that? The electric field is a vector field. You follow the discussion carefully now. The electric field is a vector field, and as such, any vector field will contain 2 points of information, namely a scalar value and second, a direction. So vector E will have a scalar magnitude and a direction. Whereas when you go to the potential part, a potential is a scalar function only, as a scalar potential. If it's a scalar, it will come with only one thing, namely the magnitude, not the direction. So basically, when you want to go to the scalar formalism, you want to make your mathematical task easier. If you want to work with the electric field vector, then continuously you shall have to keep worrying about what about the direction, keep a track on the direction. But you'd rather be working with a scalar to make your mathematical task easier. Or is it that much easier, has become that much easier? Well, you're doing mathematics, and mathematics has got absolute logical rigor. You can't escape something. What is it that you have not been able to escape? When you are working with the vector quantity, namely E in this case, then you are working with the first order differential equation. Divergence, it's just, what is it? Del x of Ex plus del y of Ey plus del z of Ez. You're taking the derivative only once in the divergence operator. You are dealing there with the first order differential equation. But when you work with the scalar quantity, your first order equation that you had working with the vector, it will now be a second order differential equation. So a price has to be paid. You have reduced working with 2 points of information. What are the 2 points of information? Magnitude and direction. You said, I don't want to be distracted by this whole business about keeping track of a direction all the time. Fine, you throw the direction part out of the window. You're now going into a variable that is defined only in terms of its magnitude. Fine, that is very good. But then you can't escape having to pay a price for that. Earlier you were working with a first order differential equation. Now you will work with a second order differential equation. That is the major difference between the vector approach, as in this divergence of E is equal to rho by epsilon naught, and the scalar approach, as in this case of del squared V is equal to minus rho by epsilon naught. Nevertheless, it is occasionally easy to work with the scalar formalism, and that is what, because once you know the scalar potential, as in this case V, you know the scalar potential, immediately the negative gradient of the scalar potential will give you the electric field. Remember, after all, we shall be working with the electric field and the magnetic field. And what are the four things that we shall have to do? I told you this point earlier also. The quest is to set down the Maxwell equations. And what are the Maxwell equations? You've got two vector fields, E and B, electric and magnetic fields. The Maxwell equations are simply these: divergence of E, curl of E. Divergence of B, curl of B. Those are the Maxwell equations. Okay, that said, now we shall go to uh, some extra workout on the potential formalism. Curl of E is equal to 0. Why is it equal to 0? Because E is a central function, Q by 4 pi epsilon naught R squared R cap. Now let us apply Stokes' theorem. Curl of E dot dA, surface integral, is the closed loop perimeter integral of E. But curl of E is 0. If curl of E is 0, then E dot dl will also be equal to 0. If E dot dl is equal to 0, why is it 0? The closed loop integral will be 0. If that is so, then we can immediately write E dot dl is a constant quantity. E dot dl going from A to B is a constant quantity. It's got a fixed value. Why? I have discussed this thing early in the class. I have made this point in a supplementary set of notes while talking about conservative fields. I hope you recall that if you go in a closed loop integral using Stokes' theorem, if you go over a central field, the Stokes theorem will tell you that the closed loop integral of that central field, closed loop line integral, that is, loop integral is line integral, yeah. Closed line integral of that central field will give you a 0 outcome, meaning that you start from one point, go to another point, and come back to the same point by a different route. Whatever the route you may take, you can come back there, you will not feel any difference. It will finally be 0. So if you carry a heavy suitcase from the ground floor to the top of your house and then come down from there, you would feel that you've done a lot of muscular hard work. Unfortunately, going by this idea of central vector fields, a lawyer can show that you have not been doing any work at all. A lawyer can argue that you have not been doing any work at all, and you'll not be actually able to refute the lawyer's statement. So going from A to B along one track and coming back from B to A along another track will entail doing the same work that you have. So basically, you can carry a heavy load by walking up the stairs to the roof of your house, the terrace of your upper terrace of your house, or you can carry the same load and scale up the wall. Whatever way you take, gravity is a central field. So either way, whatever way you do, it doesn't matter. The final points are only important, and that is the work you would have done. I've discussed these things. I look up the old supplementary notes on conservative fields. There, these points are discussed. So A to B, E dot dl will be a constant quantity, so it will not change. Constant quantity in the sense that it will be independent of the path. Okay, now what shall we do? We write E is the negative gradient of a scalar function, scalar potential. So E dot dl, going from A to B, E is substituted by the negative gradient of a scalar function, A to B. And then what is this thing? The minus sign stays outside. And what is this thing? By the theorem of gradients, you will have scalar grade function at B minus scalar function of A. It only matters, what matters is the difference between the value of the function at the first point and at the last point, the source point, initial point, and the destination point, the final point. Okay, and then you can put the minus sign inside also. It will be VA minus VB, but that's not really very important. I'd rather be keeping it this way. VB minus VA, this final statement. VB minus VA, you take this minus sign to the left-hand side, and it will be minus E dot dl going from A to B. So VB minus VA will be minus A to B, E dot dl. Okay. The next thing that we shall have to do is to take up the idea of a point of reference. What is this point of reference business? Instead of B, I'm writing a general point R. A is a fixed initial point, earlier, B was a fixed final destination point. But instead of B, I'm taking a general point R. And wherever I had a B here and a B here, I'm writing R here and here. Okay. Now, follow this point carefully. Do you realize what you're seeing in front of you? VR minus VA is the difference of the potential functions at R and A. I hope you are aware of the fact from your school knowledge of electricity magnetism in the laboratory, if you have worked or whatever, you'd always be told, measure the potential difference. You are measuring potential difference here, not the actual value of the potential. You're measuring the potential difference. So to measure the potential difference, you'll have to define the value of the potential at some reference point, and then with respect to that reference point, you will give the value of the potential at your point of whatever interest where you are. So what is the value of that point? Let's see. Define a position or a point P where the potential function has got a zero value. Let that point A be the point P. This position A coincide with the point P, and let A go to infinity. Fine. Therefore, when A goes to infinity, V at infinity is equal to 0. This thing, A is equal to P, P has gone to infinity, we are making the point P go to infinity, this will be equal to 0. VP is equal to 0. So the left-hand side will become VR, R, this is 0 is equal to minus, A has gone to infinity, infinity to R, E dot dl. E is equal to Q by 4 pi epsilon naught R squared, R cap. I hope you are aware of the fact that we do the same thing in gravity as well. We say that the gravitational field or the gravitational potential at infinity we are setting as 0, and then with respect to infinity, what's the work done here to bring something to the surface of the earth or whatever, all these things. So it's always with respect to infinity for these inverse square law forces that we set the 0 value of the potential. Okay. Now what about E dot dl? E dot dl is equal to Q by 4 pi epsilon naught R squared R cap. In line spherical symmetry, the line element is dr R cap plus R d theta theta cap plus R sine theta d phi phi cap. I hope you are aware of this thing. Minus E dot dl. You have a minus here and you have this E dot dl over here. We have to work on that. Minus E dot dl will be minus E is Q by 4 pi epsilon naught 1 by R squared minus Q by, this is E. And then dl is only dr. What about R d theta and R sine theta d phi? Because E has got R cap, right? R cap dot theta cap will be equal to 0. R cap dot phi cap will be equal to 0. R cap dot R cap is equal to 1. So minus E dot dl will be minus Q by 4 pi epsilon naught 1 upon R squared dr. That thing, this E dot dl is now simply this thing. So you have got minus Q by 4 pi epsilon naught 1 by R squared dr going from infinity to R. Then we'll have to take the integral over here. The integral will give you minus 1 by R. Minus and minus is plus. Upper limit is R, lower limit is infinity, 1 upon infinity is 0. And so V is equal to Q by 4 pi epsilon naught 1 upon R. Potential of a positive charge is a positive function. So there you are. Q by 4 pi epsilon naught 1 upon R is the potential due to a positive source charge. So if you have a whole bunch of such charges, a collection of charges, the total potential will be 1 by 4 pi epsilon naught going from I is equal to 1 to n. If you have n number of such charges instead of a single charge, so Qi by, you just add them all up. Q is changing, R is changing. 1 by 4 pi epsilon naught is a constant quantity. So Qi by Ri, it's a discrete summation. And so in the continuum limit, you will change the discrete summation to this 1 by 4 pi epsilon naught 1 upon R dq by R. And what is dq? I hope you have not forgotten that. Rho into d tau by R. And so this is something that follows from the principle of superposition also. The principle of superposition says if you have a whole bunch of source charges, the total force experienced by that charge is simply the scalar sum. I'm sorry, not scalar sum, simply the algebraic sum of all the individual forces of interaction between an individual source charge and the test charge. So F1 plus F2 plus F3 plus dot 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 all the way up to Fn. And what is F? F can be written as Q into the total electric field, where capital Q is the value of the test charge. So that can be then decomposed like this. And so E, all these Q's will cancel. Just let me just take this point. I'll finish in just a few seconds. I'll finish. All these Q's will cancel. E is equal to E1 plus E2 plus all the way to En. But then E is equal to minus gradient of a scalar function. Okay. So substitute all these things with this formula. Minus gradient of a scalar function V is equal to minus gradient of a scalar function V1. And all the way up to this. The negative gradient is a common operator throughout. If you take the operator out, you're simply left with a scalar sum of all the potential functions. V is equal to V1 plus V2 plus V3 plus Vn. Anyway, so time is up. I shall stop here. Next class is on Wednesday. We shall continue with the discussion. If you have anything to ask me, you may do so now. Otherwise, we can stop the session. I'm anyway stopping the recording now. Nobody has anything to ask?